Okay, meet up 1:30. Why don't we get started? Good afternoon, Research Methods.
Good afternoon.
All right, that's a great start. Today is Tuesday, and that means that we're even closer to our section exam. Yay, okay, we're all excited about that. Section exam 3 is coming up. Today we're going to do lots of hands-on work in just a few minutes, but just to remind you of how to prepare for all of this and what to emphasize. As always, this is available on the drive and on Blackboard, but I think I'd really like to point out is what information you should be focusing on more than anything else. And these could be the videos and the PowerPoint lecture notes from October 28th. As we're ending today's session, I'm going to give you a handout that I hope will prepare you for tomorrow. I'll ask you to do some particular reviews of these PowerPoints and videos and bring that information to class tomorrow. More about that later on. That's the information that we're going to be emphasizing. Of course, there's some cumulative nature to the work that we do in any kind of research in this class, but that's where the emphasis will be. All right, what I'd like to do is spend most of today computing with some hands-on exercises. But before we do that, I thought what we would do is go through just a little bit of the PowerPoint that we didn't quite emphasize yesterday. This is the 1118 PowerPoint, and we got through most of it, but we didn't say very much about this portion on Excel. And so I thought I'd just go to slide number 34 in case you want to play along. In fact, why don't we go to slide 35 and give you a little overview about one example that I hope will set the stage for the computation that we're going to be doing today. So here we have a factorial design. It's a 3x2. And in this particular case, we have 3 levels of feedback. We have praise when you're solving this puzzle. We have criticism when we have silence. And then we have these puzzles that are relatively simple or complex. We have a 3x2 from here. What I wanted to warm you up with is this idea that when we have an A by B design, we can talk about the different levels of, say, factor A being level 1, 2, and 3. And we call those levels A1, A2, A3. And for our B variable, our B independent variable, we might have 2 levels. We can call them B1 and B2. So just to make sure that we all yell out the coordinates of praise complex. I think I heard A1, B2. People following that, right? So we're in the first column, second row, A1, B2. Who's okay with that? Okay, all right. And so as we get into computing these factorial designs, you might imagine that we can have A's and B's and C's and even more variables. Each one will also have its subscripted number so that we know which cell we're in when we're in these very complicated kinds of designs. Right, so that's the first notion about all of that. And then what we're going to wind up doing in just a few minutes is we'll take in a 3x2 our 6 conditions and we'll have them in a columnar manner. We'll have all the data points. Here we happen to have 5 people, and we'll have the data points listed in columns. And what we'll eventually wind up doing is getting some sums for all of these and creating a new structure for us called the AB matrix of sums, which is shown here. And so I've done this on the video, but I'll do it one more time just so you can see where these numbers come from. You do it with me. 7 and 8 make how much? 7 plus 8 is 7 plus 8 is how much? 15. And then we add 6 more. 21, right? Okay. And then we'll add 10 more to that, and we're at what? 31. And then we'll add 7 more, and we are at 38. Hang on. Okay, and there's our 38. Okay, so praise complex adds up to 38, and we can do that for each of our 6 different columns, and we get the sum for any given condition. We can take column sums, we can take row sums. You can see that this is eventually going to be tying to our basic ratios for factor A and for factor B. Remember that basic ratios help us to get the sum of squares. Okay? We're going to get this AB matrix of sums, then we're also going to have a squared version of that to help us get the sums of squares and the basic ratios. And I hope you'll now take this out from the other day. We'll be working with this in just a moment. We've got a whole list of basic ratios. You might remember that we had y's, a's, and t's the very first time that we did this. And then fairly recently, we've done others. A couple of extras here. Fairly recently, we've done others. We've had, for example, S. Does anybody remember what the S basic ratio did for us about a week ago when we computed it? The S basic ratio. So within subject design, if that helps. Why do we use within subject design to start that way? Why do we use repeated measures or within subject design? So primary motivation. Okay, we can eliminate consistent individual differences, and that's what the S basic ratio did for us. It helped us quantify consistent individual differences, so we can pull them out of our denominator and get a more sensitive test. And that was the motivation for doing that. So now we have more than Y, A, S, and T. We have a whole list of them. We have Y, A, B. A, B is going to correspond to our interaction term, A and B, and then finally T. So lots of basic ratios here because the research design has gotten more complex now. We've got factorial design, we've got a 3x2, so a factor A, a factor B, and the interaction. So these are going to be the new items that we'll have, A, B, and A, B. Right. And then this is just one sheet for one side of your handout from the other day, various basic ratios. Here's how we combine them. Simple differences and so forth is following that recipe to help us get the sums of squares, and then away we go inside of our F table. All right. Questions on any of that? Yeah, please.
On the exam, will you give us like that sheet so
Yes.
we'll be able to see S for main effect is A minus T and those kind of
That's right.
things?
Yes,
Okay.
you never have to memorize these. I have
Either side? Okay.
Either side, and we have, actually we've had so far 3 flavors of this. We started out early on when we began talking about ANOVA. We had an independent subject design that was in one plane, and only one independent variable. And we had one of these, and then about a week after that, we introduced the individual differences that we can quantify. We get one of these for that, and you'll get this one. You never have to memorize these. If you take my upper level course, you will not have to memorize these. I don't ask those students to memorize the primary. All right, so that's where we're going for the next maybe 20 minutes or so in our computation. So what I'd like you to do is see if you can go out to a new portion on our S drive. We have a new folder that's for factorial designs. I'll go out with you, and we'll open up an Excel file there. We'll dial into our class, resources, practice problems. And when you get that far, the new folder is two-way between subject and motives. And as you're doing that, I'll just mention that we can, this is probably as far as we're going to go with computation. We'll have a few other computations when we come back from Thanksgiving, but this might be our most complicated computation. You can see it's a pretty busy handout that we have here. And when we have a two-way ANOVA, we can have both variables be within subjects, we can have one within, one between, we can have both in between. Believe it or not, the simplest computationally is the one that we're about to do, and that's going to be the two-way between subjects. So if you now click on that, you'll see there are a couple of different Excel spreadsheets. We want the one that says factorial between subject exercises. We don't want the one that has the word SPSS. We want the one that says between subject factorial exercises. And when you click on that, hopefully you'll get something like this. We'll see people corroborate that they've navigated all of that. Who's able to find that? Anybody not getting it? I think we're all there. All right, so this is going to take a little while, even though it's a relatively straightforward computation and relatively straightforward design. You'll see that it does take a while once we have more than one variable. So the first question, just to get us oriented a little bit, was that we had a 3x2 a moment ago when we were looking at the complexity of the puzzle that had to be solved and the kind of feedback that people were getting was the 3x2. If you take a look at this, it's differently laid out, but I wonder if somebody can yell out the dimensionality of this study. Might be able to figure it out by perusing the information up on the screen or in front of you. I think I hear it. Oh, it's not. It's a 3x3. So this one's not a 3x2, it's a 3x3. Right? So, and what we have here is going to be 5 persons per condition. Okay? So we have 5, or at least 5 scores per condition, and then we have 3x3, so a total of 45 scores there. right, is what's going on. This is entirely between subjects, the 3 levels of factor A, whatever that might be. You can think of it, if you like, as being kind of feedback that you're getting praise, you're getting some kind of criticism, or you're getting silence. And now maybe we have 3 levels of our complexity variable. We might have a simple puzzle, a moderate puzzle, and a difficult puzzle. So that's our 3 by 3. All right, what we'd like to do is we might spend a moment on the various hypotheses. We'll do a few of these, and you'll see that if you wanted to be very formal about all this, maybe we'll be formal only for today, and we won't always request this of you, but we'll see if we can get null and alternate hypotheses for factor A, factor B, and for the A by B interaction. You'll see that there are different kinds of wordings that we can use here. So let's assume that we want to do the null hypothesis for factor A. We'll call it HOA. Okay. And let's all yell out our favorite prepositional phrase. Wow, good population, okay? And we can do this a couple different ways. We might say something like, the means will be equal across all levels of factor A. Okay? So if you'll type with me. The means will be equal across all levels of factor A. And spelling doesn't count. It's okay if it doesn't count. I made that about as big as I can get it, and I also have a fairly large expanse there. So can people on the back see that?
Yeah.
Crank it up a bit. All right, really good. Maybe this helps a little bit.
Yeah.
All right, that's looking a little bit better. Okay. All right. This is an easy one. Let's drag that down so that we get a duplicate of it, and we'll turn it into the alternate hypothesis for factor A. H1, and so in the population, the means will not be equal. And we'll put that in. Okay, and I can see that we're going to have factor B will be the same kind of a thing, and we'll have that for the interaction. I think we might need a couple of more rows. So what I'm going to do is I'm going to ask you to click right on the number 4. I don't think we've done this before. Can you click right on the number 4? And that highlights the entire row. How many people have that? No? And then if you'll join me by going up to the upper right-hand corner and clicking on Insert one time, we get one row. We click on it the second time, we get another new row, creating a little more space for us to get even more hypotheses. How many people are able to do that? Did I lose anybody on that transaction? I think we're all there. Okay. All right, why don't we just copy these down? Why don't we swap out the A's and B's? Okay, so I'm going to say Control C, Control V, and now I've got too many hypotheses for factor A. I'll cross out the A's and put in some B's. So structurally, this is always the same thing. In the population, means will be equal across all levels of factor B. There's our alternate hypotheses. And you might remember that we're always really evaluating the null hypothesis using modus tollens. Anybody want to recall for us the structure of modus tollens? If you can, about the P's and the Q's. Have that nice. Yell it out if you know. If P, then Q.
If not Q, then therefore not Q.
All right. If P, then Q. Not Q, therefore not P. Okay. And we apply our P's and Q's only to the null hypothesis by convention. Okay, we've got a couple of more that we can do here, and we'll copy down our latest structure. I might even put in one more row of blank, just so it's visually a little bit distinct. And now we can change this to the A by B. This one's going to be a little bit different. There are different ways of phrasing this. So we'll start out within the population, as always. And we might say something like this. In the population, the effective factor A, get rid of that, the effective factor A, and then I'm going to add something in parentheses here. When we're talking about the effective factor A, we're talking about the differences across the levels of factor A. So that's really what we mean when we're talking about the effective factor A is, are there differences across factor A's levels? And this will be the same across levels of factor B. So that's a bit, and I'll read that to you because I realize some folks are running out of space here and I will see all that. In the population, the effective factor A, and then parenthetically differences across levels of factor A. will be the same across levels of factor B. Make that nice and big for the folks in the back of the room to see it. Actually run out of space. I am going to pause there just for a moment and ask for people to indicate either verbally or by hand if you've got a freehand and you're not typing. We're going to versus subtraction method. Subtraction method for finding interactions. This is really a way of stating that the subtraction method is going to produce zeros across levels of factor A at each level of factor B. Okay, so we start differencing the levels of factor A. We're going to get zeros, or at least we're going to get the same differences at all levels of factor B. It's really a formal way of stating the subtraction. Who's okay with that? Is anybody confused by that null hypothesis? It's really a statement about having identical differences, but having different differences. And once we have that long and winding phrase, why don't we copy it down one more time? We'll change it into an H1. And we'll just add our usual knot. In the population, the effective factor A, differences across levels of factor A, will not be the same. And that's calling for then different differences. So the null hypothesis says same differences, Philip's hypothesis says different differences. It reminds us what we're going to be testing and how we test for interactions. Who's okay with all of that? Okay, all right. So thanks for bearing with that. I'll put those in a fancy color. They wouldn't have to be, but we'll just set them off a little bit. Trying to make them, maybe that's worse. I don't know. Maybe it was better in black. It gives us higher contrast. Okay, a couple of things here. We're ready to go on and do the raw scores. Typically, when we have raw scores, we have to get a whole list of squared scores. So why don't we do that much? And it can be advantageous to just take advantage of the entire structure, make a copy of it. So now I have two sets of raw scores. They're identical to each other. I do that with a control C and a control V. And then what I'm going to do is change the word raw scores to squared scores. And now I need to change these to the squared versions of those numbers up here. So that 7 that you see in A1, B1, I'm going to say equals. I'm going to click on that 7, and I'm going to square it. I'll take advantage of the caret over the 6, and I turn that into a 49. I drag that down. I drag that over. And I now have a squared version of what was on top. And I'll wait for you to catch up with me. But you should have 49 in that corner or 16 in that corner. And by a show of hands, how many people have a squared version of our raw scores? Right, so not everybody's signifying, so we'll wait just a moment. We have several computations here that we don't want to lose here. So you can jump in on your neighbor. Please go ahead.
I just have another question. It may not be related, but so I remember reading that like the simple main effects are the like interactions of, for example, like level A at one level of level B. So is that what each of these are? Are those the simple main effects? If it's A1 at B1, A2 at B1, does that make sense?
Yeah, I think I'm following your question. We're not quite to simple main effects yet, or to simple effects yet. We will look at simple effects if it is the case that maybe we have a significant interaction with do that. All we're saying is this would be a particular cell in our 3x3 structure. So this might be, for example, praise and simple. That's all that.
Okay.
Oh, I see. So you were thinking this might have been a simple effect. It's really just one of the cells.
Okay.
All right, really good. All right, show of hands. Who's now got the squared scores? Okay, is that working for us? I think we're just about all there. One other step I want to take, and we haven't done this before, but we now need to do this to get to our new idea, which we saw in PowerPoint, is called the AB matrix of sums. What we need to get somehow is a set of sums for even the raw scores. So I'm going to go back just a little bit, maybe by a few rows, and if you need to insert a row, feel free to click on one of the numbers and insert yourself a row, or delete yourself a row, as you see fit. And what we'll do is we'll start here and say equal sum. And I'm now going to take the sum over these, and I'll close that off. And who remembers getting 38 before? Okay, we did that one. Okay. So we'll get a sum of 38, and then if we drag this on over, we get the sum for each of our different 9 conditions. Why 9? Because we're a 3x3 research design. Then we can label these as we like the sums. We won't need to do this for the squared scores just yet, but we have now the sums and we have the squared scores. Okay. Who's got all that? All right, looks like the whole gang is doing this. All right, now we're going to do something that we haven't done before. We're going to try to create that brand new AB matrix of sums. And in order to do that, we're going to click on A1, and we'll start creating this matrix. We'll put in an A2 and an A3. And then we'll also go over here, one column to the left of A1, and we'll put in B1, B2, and B3 going down. Looks like I had some previous formatting here. I'll get rid of that formatting. You can leave it there if you want. You don't have to keep it. Maybe I'll center that. Maybe I'll center all of these. And we'll call this the AB matrix of sums. So we're creating a 3x3 structure. A1, A2, A3 in the columns, B1, B2, B3 in the rows. Who's okay with that? All right, now here it gets a little bit tricky. What we want to do somehow is fill these three cells with everything related to B1, the A1, the A2, and the A3, all within B1. And you might notice from up here that these are going to be the first three that we have here. We have B1s in favor A1, A2, and A3. Who's following that? Have you seen it? So if you highlight that with me, and this might be the easiest way to go, you can just drag it on down. And this is a motor skill, so we'll see if people can drag it without creating any new numbers. So now we've got three sums in the appropriate places. Again, the way I dragged that was in the center of that rectangular structure, not off to the side, not off to the corner. We'll do this one more time. If we take the next three, you might notice that that's the B2 family. And we'll slide that down into place. And then finally, we've got the A3 family. We'll slide that down into place. And we'll see how many people got that. See if anybody got stuck there. We're sliding these around. And we now have the sums that we were talking about a moment ago. So this will be the sum of A1, B1, and so on to our 3x3 matrix. Okay, so all we have here is the sums. Why don't we now see if we can get some column sums and also some row sums. So let's do some column sums. I'll put in COLSUM. And all I need to do here is a full sum. And I'll highlight over those three. And I come to a sum of 93. And I can drag that over. Once I have that genotype, I can take advantage of the spatial relationships coming down the corner, drag that on over. I did 93, 59, and 71 as my three column sums. And I'll ask for a show of hands to confirm those numbers. Okay. All right. Wait just a moment because I think a couple of folks are still catching up. Some idea about what our next step is going to be while we're waiting for some folks to catch up. Our next step is going to be after the column sums.
Row sums.
The row sums, okay. And so the column sums are really telling us about a factor A. And it's good to notice, by the way, it looks like we're getting some differences. Whatever A1 corresponds to, it's generating higher scores than A2. That might turn out to be significant. It might turn out to be non-significant, but we'll find out. Row sums. And again, looks like we got some formatting here. I can get rid of that. I'll leave it in, that's fine. And now I'll say this is equal to the sum of my neighbors to the left. Three of them here. And I can drag that on down. And even into the corner. I'll get rid of that formatting. And I wonder what a grand total of 223 with the corresponding sums of 96 and 61 and 66. All adding up to 223. Who's got all that? Anybody stuck? Help your neighbor out. We've got the row sums and the column sums. Okay. So now we have our AB matrix sums. This is new. This is something that we have to do whenever we have an A by B design. Here we happen to have a 3 by 3, but we could have had a 3 by 2 or a 4 by 9. Could have been any two numbers. All right. Can we make one copy of all of this? Let's highlight it. We'll do a Control-C. We'll make a copy of that. Anybody have an idea what we're going to do with this copy? Or our second copy? What do we usually do with our second copy? Okay, so now what you can do is get rid of all of these numbers that are in this second copy. We'll call this the squared AB matrix. Just so we can keep them straight. And just like before, we'll go into A1, B1, and this cell will be equal to its square counterpart for the raw AB matrix cells. I think I see.
Just whenever I copy and paste like these types of charts and stuff, and then I paste it, it always, the numbers they just go to zero. Like 38, 35, like all of those numbers just.
This number went to 0?
Yeah.
In your pasted one or a voted?
And my pasted one.
Your pasted one, okay. Good news, we can get rid of everything in your pasted one because we need to recompute those anyway. Okay. And we'll give you a moment to do that. Is that working for you, Kate? You just hit the delete key on each of those, and we'll go back to an open cell. So this will be equal to, now we can dial up to the 38, and we can square that. And I come to a 1444. Can you confirm that number? Okay, very good. And then if you drag that down and over, drag it down to the column subject, drag it over. And a note about this, a few folks in one of the recent computations, it might have been a homework assignment, I'm trying to recall where I saw it. Some people correctly computed these and then summed those. This number should simply be a squared version of that 93. Okay, that's all we have there. Okay? And we wind up with a total of 49,729 in the lower right corner of our square AB matrix. Proof we confirm 49,729. Okay, looks like we're all there. Okay, thank you for bearing with that. Now we're almost home free. We can start with our basic ratios. And now we can really start taking advantage of the sheets that we have in front of us. We might expand cell B just a little bit, give us a little more room. And why don't we put in basic ratios that are right down in this sequence? We can put in Y first, then AB, then A, then B, then C. So we're just going to put in those letters. We'll do Y first, then AB, then A. And by the way, I'm going to pause and see if you get what I get. I put in a Y, I put it in AB. I put it in an A and it gave me a B. Anybody have that scenario? Okay. So sometimes the Microsoft programmers think they're smarter than you are, and they're not. They think that, oh, you're going to put it in AB a second time, when in fact you're not. So if you have that, you can hit the backspace one time, and that will just bring it back to an A. See how many people are able to do that? All right. And then we can put in our next basic ratio, you tell me. B, okay? And it thinks that you want to spell out basic ratio, okay, but you can put in the backspace and there's just a B there. And then our last basic ratio, can we yell it out?
T.
T, very good. And I'm going to center these even though you wouldn't have to. That's great. Compute these basic ratios, Y, A, B, and T. All right. Who's ready to go? Yeah? Anybody need another moment? Okay, we do. All right, so let's just remind ourselves of what the Y basic ratio is. The sum of the individual squared scores. Maybe I can remind you where all of those are. Those are up here. We have all the individual squared scores in that 9-column structure that we have up here. Why don't I turn that yellow, just so you can see where I'm going to be highlighting. Okay? So we want the sum of those yellow items, and we'll say equals sum. So this is for the basic ratio of Y. Sum. And I'm going to highlight over that range that went from 49 in the upper left corner to 16 in the lower right corner. And I come to a 1445. And we'll see if anybody can corroborate that. Okay. All right, looks like most of us are there. Really good. All right, now we're going on to AB, which we haven't computed. Let's take a look at what the formula says. The sum of the individual cells from the squared AB matrix divided by the number of subjects per condition. First, can we remind ourselves of the number of subjects per condition? Okay, 5. That's going to be really good. And we also want the individual cells from the squared AB matrix. Why don't I put those in a slightly different color? We want these central items here. Okay? And again, that's right from this formula sheet that some of the individual cells from the squared AB matrix, maybe if I put it in a light gray, will still be pretty contrasting with folks in the back. So this will be equal to the sum the individual cells from the squared AB matrix, that's the gray area that I have here, divided by, you tell me, what is it? 5? And I wind up with a 1292.6. And I'll pause, save that. Some people are all right with that, 1292.6? Okay, really good. All right, let's go on to our next one. You might remember that we're going to wind up doing these columns for factor A, and then those rows for factor B is basically what we're looking at here. So this is the basic ratio A equals the sum, and we'll go across this area. And we have to divide that, interestingly, by the number of levels of B times the number of subjects per condition. So what's going to be our divisor here? 15, okay? And I'll spell it out like this. You can put in 15 if you want, but I'm going to say 3 times 5, just so people know where those numbers are coming from. And I wind up with an 1144.7. And just so everybody is okay with this, I'm going to make that a slightly different color so people can see where I summed. I summed over these items in red. I'll turn that red. And I divided by 15. Yes, please.
Mine is automatically rounding.
That's okay. If you wanted to play around with how many digits precision you get, up here, Catherine, you might see that you can click left or right. And I don't know, for some reason I'm rounding to 1, but I think the rounding is 1.
Oh, there.
Okay. Now, one more time, we're going to that was factor A, right? That was the basic ratio. The sums of squares for factor A, we were doing that by pie chart the other day, right? So now we've got sums of squares for factor A. Now we need to move over and get those for factor B. Those are conveniently listed in rows. So we'll say equals sum, and we'll highlight over these row sums from our square AB matrix, and we'll divide by the number of levels of factor A times the number of subjects per condition. That's what our formula sheet does. So what are we dividing by? What number? Yellow down. 15? Okay, one more time, it's 15. It turns out that we happen to have the same number of levels in these two variables. So I'm going to divide by 3 times 5 is 15. And I come to an 1152.87. Now we'll see if anybody can corroborate that. Yeah. I might expand this a little bit. All right. And why don't I make that one slightly different color so people can see where those numbers are coming from. I'll go with those purple colors. All right, and then we're off to our basic ratio T, and we've done this one before. This is the grand total squared, and this is interesting, divided by capital N, which is going to be lowercase a times lowercase b times n. So before we get into this, consider to figure out what is that all equal to? Lowercase a times lowercase b times n. 45, right? Because it's 3 times 3, 3 levels of factor A, 3 levels of factor B, and then you're going to have a total of 5 people in each of those conditions. So 3 times 3 times 5 is 9 times 5 is 45. Okay? So that's going to be equal to this grand total that we have here divided by, and you can put in 45 if you want. I'll try to be literal and put 3 times 3 times 5. I've got that right. You should wind up at 1105.09. It helps you to expand your column C a little bit so you can see those numbers. That's fine. Within rounding, who has those numbers? Who's anybody on 1105?
Can you just go back to B?
B.
I could.
Okay, so B is in purple. Sorry, that's not a salient purple for you. B is going to be the sum of these purple guys divided by 15, which was levels of factor A times 5, excuse me. 3 times 5, that's the 15. So hopefully this is sufficiently color coded. I guess I can give us one more color, or at least I'll bold that. Those two go together. And that was this number divided by 25. A times B times N. All right, one more time. Who's okay with that now? All right, we come together pretty well. We come together pretty well. All right, I'm going to save that, and we'll go on to our next page. We have basic ratios. What do basic ratios help us get? Sum of squares. Why don't we put SS here? And we'll start to build our table. What comes next to the SS in the F table? Can you all yell it out? Degrees of freedom, and next to degrees of freedom come mean square, which is also called the variance, and then F, and then maybe some kind of sig value, which is also a p-value. I think we'll go that far for now. And remind ourselves that we have in this F table, because it's a 3 by 3, we have a factor A. We'll have a factor B. These were different colors on the pie chart the other day. We have that big pie chart. We have the A by B interaction. A by B. You can say interaction if you want to. And we'll have some kind of an error term. Now I'll center those. I'll save all that. All right, so all of that work so we can begin to get the variously colored portions of our sums of squares pie. Okay, factor A. All right, now it's time to flip this over. Okay, okay, and start working through the second page. And we're just going to mix and match our basic ratios. So this will be equal to A minus T. Okay, and that gives you a 39.64. First, who can corroborate that number? And then can we remind ourselves, why do we exhale at that point? It's not negative, okay? So this might actually be a wrong number, but at least it's a plausible number, right? It's non-negative. Let's do the same thing for B. And it turns out that's going to be equal to the B basic ratio minus the T basic ratio. It's nicely aligned for us right above the sums of squares. I get 47.7 and some change. Corroborate that number. That was B minus T. Okay. All right, now this is the one that you always need to be careful about. Remember that there are several minuses and one plus sign here. We're getting the sum of squares for the A by B interaction. This will be equal to AB minus A minus B plus T. I'll leave that there. I'll let you hit enter and yell out the number that you get. 100 and just a little bit of change. Right. 0.08, depending on how far you've rounded. Probably 100.09 or something like that. Okay, and then the error term is going to be y minus AB. So equals y minus AB. And we wind up with a 152.4. And again, we read the side of the because now all of our sums of squares are going to be non-negative. At least they have to be non-negative. You could wind up with a 0, but you can't wind up with anything. Not in the real number system. Okay, who's with us? All right, now we're on to some really easy computations. Can we all do this in our head? A minus 1 is equal to 2, because we have 3 minus 1. Okay. Same thing in this case for factor B. That's going to be 3 minus 1 again will be 2, because we have 3 levels of factor B. I'm going to center everything in my F table. Now we have A minus 1 times B minus 1. That's actually this computation times that computation, and we wind up with 4 degrees of freedom. And then we have a longer computation. A times B times n minus 1, and that's lowercase n. So this is going to be equal to 3 levels of factor A times 3 levels of factor B times, and I'll do it literally 5 minus 1. And I wind up with 36 degrees of freedom in my denominator, which is my error term. Who's okay with that? I said we can call that the error term. If you prefer to call that the within subject variability, that's the same thing. 2 different versions. And in turn, we're going to wind up putting factor A over that, factor B over that, and the A by B interaction. This would have been the red area that we had in our pie charts together. Okay, so why don't we go ahead and say that our mean square is always the SS divided by the PF. And we can build that phenotype to the phenotype once and drag it down. We need to roll all that. All right. And then what we can do is start forming our ratios. These are starting to look pretty good. We have ratios that are looking like they're going to be bigger than 1, so we've got a chance at significance. This will be equal to factor A mean squared divided by its error term. And then factor B divided by its error term. And then the A by B interaction divided by the error term. And I'm coming up with F ratios of 4.6-ish, 5.6-ish, 5.9-ish. If you can corroborate those numbers, can you raise your hand? And most of us are there. We'll give a moment or two to others who are still catching up. While we're catching up, I'll just mention that you can always click in this over that, this over that, and this over that. Or if you wanted to, you could do this over that, and then you could freeze the coordinates for the denominator. And you could slide in your numerators over that closing denominator. How do we freeze? Anybody remember what symbol we use from the keyboard? Yell it out. Dollar sign. So you could do that if you wanted to. Okay. One more show of hands. How many people have these numbers? All right. All right. So we've got the mean subject factorial F's computed. Congratulations. Why don't we find out if these are significant now? And to do that, our Excel command will be equals fdist. Okay. Equals fdist. And we put in the F value, the degrees of freedom for the numerator of that F, that's going to be 2. The degrees of freedom for the denominator is going to be 36. Right, Corinne? And we wind up with a sig value that's going to be less than 0.05, so we're going to wind up rejecting that one. And And I'm going to pause. How many people can confirm that number? Within rounding 0.56.
I have a question. Why was the second degree of freedom of 36?
Yes, thank you. Okay. So if you'll remember, Rachel, what we did in order to compute that f, it was an f ratio, and it was this one over that one. Remember, of course?
Yeah.
And their corresponding degrees of freedom are 2 and 36, okay?
Okay.
All right, and then we're going to do 2 and 36 again, then we'll do 4 and 36. All right, good question. Equals f this. Why don't we do the same kind of a thing for factor b, but we now have to put in the observed f factor b. It so happened to have the same degrees of freedom. It didn't have to be that way, but that's how it turned out. Wind up with 007, just like in the movies. Okay. And that means, of course, we can reject the hypothesis. And then we'll say f this one last time. This is for the interaction. And this time it's going to be 4 and 36 for the corresponding degrees of freedom. Wow. So we wound up with a significant effect for factor A and for factor B and for the E by B interaction. Who's okay with all that? Okay. Any questions on that? Okay, we could get the critical values, but I think we don't need to get the critical values. I wonder if we might do a couple of things. Now, why don't we see if we can get, just for practice, can we get the eta squared values? Okay. So why don't we call this one eta squared? Now, we introduced this yesterday for the first time. First, who remembers doing this yesterday, even if you don't remember the formula? Okay, all right, good. So we do recall that one. All right. Does anybody want to take a chance at roughly what that formula will look like and how we might begin to compute eta squared for, say, factor A? Anybody want to yell out an idea? I'll give you the equal sum. Okay, thanks.
So you do the factor 1, 5, and 4.
Okay, and what component of the factor? So factor A, for example, is a lot of numbers in the factor A group.
Would it be the SS?
Yeah, okay, right, the SS, right, okay. So we're going to take that one. This is the SS for factor A. That was really good at. And then do you remember how the rest of it went? Or maybe you don't?
It's over SS plus the error.
Yes, right, okay. Is that what you were going to say, Sasha? Sasha? Or do you have a different question?
Oh, no.
Okay, all right. So we're now going to put that over, and I'll do this parenthetically. We're going to do that same number one more time. For me, that turned out to be cell C49. That may or may not be your cell number. Plus, Hannah was correct, we want to pick up the SS for the error term. That value is 152-ish. And I'll put a right parenthesis in there. I'll let you hit the enter key. I'll leave this up there so you can see we're taking the SS for the effective interest over that same number plus the error term. Right? So this over that sum. I'll let you hit enter and call out what you get as your eta squared. Can you get out whatever you get? 0.2-ish? 0.206 or something like that. Can somebody help us with the interpretation of that? What is up there? So we get a 0.2 there. What did we say that meant? What is it? Okay, relationship among the variables. Eta squared is a measure of effect size. So it's telling us about the strength of the relationship among the variables. Okay, does anybody remember the range of eta squared? It goes from what to what? 0 to 1. Okay, so 1 would mean they're perfectly correlated. There's a very, very strong association. As goes factor A, so goes the dependent variable. That's what 1 would mean. 0 would mean there's no association. This means we're explaining about 20% of the variation, 26% of the variation in our DV based on factor A's distribution. Who's following that? All right, can we do that just twice more? So same kind of an idea that Hannah had given us. This will be equal to now the sum of squares of factor B divided by that quantity. So we'll put this in parentheses, same number again, plus the variability that was entirely within subjects, we'll call that the error variability. I'll let you call out the number that you get. Okay, so this was a little bit bigger, right? This is now accounting for maybe 23% of the variation in that particular comparison. Almost 24% of the variation. One last time, we'll do the effect size as mixed by eta squared for the A by B interaction. Combined effect of these two independent variables. It's going to be equal to this, divided by quantity, and plus, as always, that. And we have something like 39%. Who's got that number? Okay. All right, really, really good. Okay, So now we have F values for all of these. We know there's things. We know that we're going to wind up rejecting in alternate cases. We can even say something about the magnitude of the influence each of these factors is having on the defender. Questions so far? Okay, why don't we do this? Why don't we go over and why don't we write some formal APA style statement? Put an APA style. And we'll do something like this. We'll tell the reader which statistic we had computed. What statistic did we compute? We all yell it out. The F statistic? Okay, all right, good. We computed the F statistic. And how many degrees of freedom do we have for factor A? 2 and 36 is what we typically record. Okay? And our observed value was 4.68. Maybe 682. I might go that far. Our p-value was 0.156. And we might reject HO. You can say reject HOA if you want to, but only reject HO. And then we can take that structure down one more time for factor B, which happens to have the same degrees of freedom. We got lucky on that. We'll slide in factor B's observed value of M 5.643. Value is going to be 0074. Maybe 007 reject HO. Equal sign. And we'll do this one last time. We'll copy down the structure and we'll just tweak it. Here we happen to have 4 and 36 degrees of freedom. Our F value for the interaction of the combined effect factor A and factor B was 5.9. This is interesting. Do we truncate or do we round? I won't make a big deal of it. I will tell you my own personal style. I prefer to offer very conservative representations of my statistics. So I didn't really make it to 5.91. So I would typically truncate this and tell the audience that I only got as far as 5.91, and that way if they challenge me, they'll say, did you really get that far? And I actually got over it. Okay? Right, so we're being fairly conservative about that, but I won't make a big deal of how we round numbers. 5.910. And then our p-value is 0.009, and we wind up rejecting the show. All right. I'm going to save that. Okay. How many people first got all of that? Any questions? Please.
Can you please redo the degree of freedom? So you explained it for Rachel, but
Sure. So the question is, how did I come to?
Yes.
Okay, thank you, very good. So thank you for that question, Brittany. So what happens is, when we're reporting an F value, we always give the associated degrees of freedom. Yet, the statistic, by the way, looks like this, is that positively skewed. And the extent to which it bends depends slightly on the degrees of freedom. Even if you change from 2 and 36 degrees of freedom to 3 and 30, it bends slightly differently. It changes where the boundary is for statistical significance. So we always report to the reader what our degrees of freedom would be. And our mean square for factor A was here, and our error term was here. The corresponding degrees of freedom were 2 and 36. For factor B, the corresponding were 2 and 36. And for the A by B interaction was 4 and 36. Does that work for you? Okay. All right. Here we go. Well, I was going to have us do some work inside of SPSS, but we are now at 2:17, and you've been fantastic. You should think of this as a masterpiece, having manually computed a 3x3 factorial design and a fully developed F table with power, with beta squared and with APA style. You feel really, really good about it. So what I'll do is I will give you 2 minutes off of your behavior, but on your way out, I'll ask you to take one of these sheets, and in preparation for tomorrow, this will not be very formal, but I'll ask you to think about each of the 7 different PowerPoints and each of the 7 different videos that we've had since October 28th inclusive. And I'd like you to just maybe look over those and identify 1 or 2 things that you can teach me about in those PowerPoints. And you might just note down that in the October 28th PowerPoint, we had slide 3. I'm comfortable explaining that to you in slide 6. You can make a note of that. And then I'll call on people randomly tomorrow to teach me, and this will help you review for Friday's exam. Okay, so please take one and pass. I will not grade this. This is really just preparation for you. And feel free to go, and I'll answer any questions that you might have.
I have a question. We didn't have a computer quiz before this exam. We had like a lot of like competition.
this is still going to be mostly conceptual, not application.
Okay.
This stuff that's going to be application will be on your next computer exam after you get back from the.
Okay.
All right, that's great. Anybody got that one? All right, thanks for a great session. Look forward to hearing it tomorrow. Hopefully, we can prepare well. Yes, please do. I'd like to put down the slide. That's yours. This one? Also, for just in case you ever misplace that, that's available to you out on the slide.
Hey, Megan.
Yeah, like, I don't, you study that? Is it funny if you can know something? I don't. Ships at work. That's what time's the cab review? Have a good day. Tissues.